Today we're going to talk about deep neural networks. I briefly introduced this in the surrogate modeling section, but we didn't have time to go through it, so I'm going to go through it today. We're going to look at it in the context of surrogate modeling. And so if you recall, that means we're going to have a bunch of data points. So let's call those our xi's. These are our variables that describe the data. So let's say I've got some airplane and I've described it in some way and its conditions or whatever. And we've also got labels, and these will be FI. So let's say this is the drag of the airplane, and I want to be able to predict the drag of the airplane as I change it or look at different operating conditions or whatever. So I've got a whole bunch of these data points and a whole bunch of labels. So this is called supervised learning because we've got labels. And I should say that neural nets can be used in all sorts of contexts. They could be used with unsupervised learning or self-supervised, and in other things beyond just regression that I'll talk about today. But this will be just kind of a vanilla deep neural net introduction. Okay, so we've got this data, and we talked about kind of these simple, it's only easy to visualize these in 1 or 2 dimensions, but some sort of surrogate. I want to be able to do this in high dimensions with lots of data, and neural nets, deep neural nets, are a nice way to are nice in the sense that they provide a lot of generality, right? So some of the surrogate models we've looked at, like polynomials, assume very specific forms, and if our model really fits that form, that can be very efficient, right? But sometimes we need a lot of flexibility, and neural nets provide that. The basic idea is that we could chain together a lot of functions, right? So let's say I have a simple function, f1 of x, but then I chain that into another function, f2 and f3, and so on, right? That I can take a very simple function, but if I layer it, I can create very complex functions. So this is kind of a typical kind of picture. This is certainly not deep. This is what we would call 3 layers, 1, 2, and 3. This would be the inputs. We don't count that as one of the layers. We call these 2 layers here hidden layers. This would be called the input layer and the output layer. And as drawn here, these are what are called fully connected layers because every node or neuron here in this layer is connected to every neuron in the next layer. And again, there are many variations and possibilities. We're just going to stick with the vanilla neural nets for today. And when I first learned neural nets, this is kind of what we looked at. One of the big changes today and why it's kind of been given the new name deep neural nets is that people will use many hidden layers as we've been able to accumulate more data and have better processing capabilities. We've been able to train really large or deep neural nets. And that's made these models much more effective. Okay, so let's look at what's going to happen inside a neuron or a layer. Basically, we'll skip to a layer. So imagine I've got, we'll keep it small, one layer that's got 3 neurons, and the next layer has 4 neurons. And those are connected, right, as follows. And so I'm just going to draw a few of them, and now we're going to describe what does that connection actually look like. So along each of these connections here, we want to specify some sort of weight and bias. So what that means is in this layer, we'll call this xk, and this will be xk plus 1, right? So this will be the kth layer here, k plus 1 layer here. And this is just a vector of numbers. So the value at this neuron is just a number. This is just a different number. And I want to take these numbers, this vector of numbers, and propagate it to the next layer and get another vector of numbers. So the first thing that we could do is just a linear function here. So we could say x, actually we're not going to go to x, sorry, we'll just call this z. Z is equal to xk plus 1 times this weight matrix plus a bias, right? So this is just a linear equation. Right, so I got a matrix vector multiply and then a matrix here of biases. Okay, and so this, and I guess I should maybe be more careful. This is, oh, sorry, this is not k plus 1. This is for k, and these are the weights for k and the biases for k. So in this case, since xk has 3 numbers in this vector, and I want to get it to have 4 numbers here, and that means that the size of this w, right, w is going to be, let's see, that should be 4 by 3, right? Because I've got a vector of length 3 being multiplied here on the right, and so once I multiply it across, it'll be a vector of length 4, and that means b should be of size 4. All right, so I've got 4 biases that I'm going to add. After I multiply all those weights, I add 4 biases. I'm going to have 4 numbers here. Okay, so that's the start, but it can't be just that, right? Because if I only have linear models, and I'm going to draw over myself here, but let's say I've got another layer here, and then I connect that, blah, blah, blah. I do the same thing, and I have weights and biases over here. I can't just only have linear models, right? Because if I did that, then the next layer, Z, is going to be W times the previous layer plus its bias, but that previous layer was also Wx plus B. I'm just not putting the subscripts here just to be quick here, right? So that's going to be W, let's just call this 2 times 1 times X plus W2 times B2 plus B1. This is all just a vector. This I can just call a new W. So I haven't done anything, right? I still have a linear model. I could chain this as long as I want, but it'd be equivalent to only being 1 layer deep. So let me get rid of all that. So I've got to have some sort of nonlinearity. If I only have linear models, then adding depth does nothing for me. Okay, so sorry, I gotta get rid of all this. Okay, so I'm gonna take Z, and to get my next layer, I'm going to pass it through what we call an activation function. I'm going to take that Z here, right, and pass it through an activation. And this is going to be where the nonlinearity happens. A has got to add some sort of nonlinearity. And that's it. That's what happens from one layer to the next, right? This is 2 lines of code, and I just repeat that in a loop, going from one layer to the next layer to the next layer to the next layer. So mathematically pretty simple, but can be quite powerful because of the fact that as I make this really big, I can capture a lot of generality. I can predict actually quite impressive or complex things. Okay, so, and I should also say, when we talk about learning or training the model, these coefficients, W and B, right, we call these weights and the biases, and later, I'm just going to group them all together and call it theta. These will just be our variables that we're learning rather than keeping 2 separate things. I'll just call them theta. But these are the things that we're training for, that we're optimizing. When we're building the surrogate model, we run it through an optimizer to learn what are the right weights and biases I should have, right? So I've got all these knobs I can turn. I've got these inputs that I have or that I know, and I know what the output should be, at least for some of my data, right? Those were those Ys, those labels, right? I know I've taken my airplane and I've run through a bunch of things, and so I know what the drag should be for a bunch of cases, or maybe a drag distribution or whatever it is. And I want to compare what those are, and I change those weights and biases, and I do that across all the other training data, just like we've talked about. We've talked about cross-validation, all those kind of things where we separate training and testing data. Same kind of idea. I'm going to have a bunch of training data and later some validation data. But so these, for the perspective of training or developing my surrogate model, these are my design variables, these weights and biases. And so there'll be a set of them between each pair of layers. Okay, so what's that activation function look like? When I was a student learning about this is what everybody used. At the time, it was a sigmoid function. And so you could think of this as this way to kind of map between like firing a signal or not firing a signal, kind of motivated by a neuron, right? And it turns out that these don't work super well. And this is also why these were not super popular when I was a student. But the problem is that a sigmoid comes very flat. And so if I'm in this region, it's great. But as soon as that Z gets kind of big and I land in this flat region, that neuron just kind of dies, right? Because the gradient here is 0. And so it looks like, well, whatever I do, nothing is happening. And so it kind of saturates really quickly. Most commonly, what's used today is what's called the ReLU. It's a rectified linear unit. And it's a little hard to see this part, but it's very simple. Mathematically, it's just this. The A of Z is the max of 0 and z. So on the positive side, if z is positive, I do nothing, so it's linear. And if z is negative, I just truncate it. I just smash it down to 0, okay? And that's it. So it's barely nonlinear, but turns out that's enough. It functions surprisingly well. We might not think, in fact, part of the reason why the sigmoids were used, it was thought that it really needs to be a smooth function, but having this discontinuity here turns out not to be a problem. And we might rightly point out that, oh, well, isn't it flat here? And we just said that was a problem with these sigmoids. Turns out in practice, it's not such a big problem here, although there are variations. You could use what's called a leaky ReLU, where there's a slight slope here. And so that's an option you can use. But commonly, it turns out that actually, it seems probably it's because these neural nets are over-parameterized. They get so big, they have so many neurons, so that if a bunch of them die off, it actually doesn't really matter. There's enough flexibility there. And actually, that may be, sometimes that's desirable, that some of them drop out, it gives you more robustness. This is actually a technique that's used sometimes in training neural nets, is what's called dropout, that you take some subset of the neurons and intentionally turn them off. And then in the next batch, you would randomly choose a different subset. And so the model has to be robust in that sense, because it can't overlearn, right? It overtrain and overfit the data. And so in effect, this is what you might think is happening here, is that some of those are dropping out, and it turns out that it works quite well. Okay, so that's basically the model. So let's talk about the objective function. If we're doing classification, cross entropy is a typical one, but in engineering, we typically would look at a regression model. We got these continuous outputs. So very simple thing is just to use a mean squared error, right? So if I've got, say f hat is what I predicted from training set I, and I would subtract that from my measured value or simulated value or whatever it was, right? So let's say I've got these outputs from airplane again. I know what they are or what they should be in this training set. And this is what my model is predicting. And I'm going to take those, square them, sum them over all of my samples, and perhaps normalize it too. I don't have to, right? That doesn't necessarily change my objective, but looking at a mean value is probably going to give me a better scaling here. Okay, so that's it. Notably, in the book, we call this F. Actually, what do we call this in the, what did I write in the book? I just want to be a little consistent here with what I wrote. I guess I didn't give it a name. Oh no, I did call it F. Normally in the book, we call this objective F. I'm being a little confusing here because I've got now Fs and Fs. I guess for today, I'm going to call it J, because that's maybe more common in the machine learning community. Okay, so let's go with J. So that's it. Notice a big difference from most things that we do optimization-wise, that this is just single objective, no constraints. It's going to make it a little bit easier. All right, so let's talk about backpropagation. So backpropagation is just reverse mode AD that we've already learned about. It's minor, well, it's not really different. There's some, in a deep learning sense, the only real difference is that we typically just have that one output, right, the objective. So it's not as general as reverse mode AD. It's also a little more specialized in the sense that there are how should I phrase this? A common set of building blocks that we use, right? Like I just talked about, this ReLU, for example, and ReLU in connection with this linear model, or in classification, I might use, or I might use like a softmax function or things like that. There are these typical building blocks, and so I can get derivatives for whole building blocks, whereas in reverse mode AD, we typically look at the operation level, because what could come out is very general, right? So we have to approach it very generally, but in a deep learning context, there are more building blocks, and so I might be able to derive derivatives for an entire building block at a time. So again, not really anything different than what we've done, but I just want to mention a few things here that are maybe slightly different than we should think about. One difference is that we're taking really the same function. I'm not going to draw the connections here, but different than what we normally do is we don't have the same function. Here we've got really the same kind of function being propagated through a network a whole bunch of times. And so what will happen is that if, and this is kind of a loose way to explain it, but let's say the numbers here in my weight matrix are large, right? Let's say maybe a more specific way would be say the largest eigenvalue is bigger than 1, but let's say all these entries are large, bigger than 1, and that occurs everywhere here. Then I could have some numbers x here, and as I go through here, things just keep getting bigger and bigger. Imagine I take a number that's a little bigger than 1 and I multiply it through again and again and again and again and again, right? It's going to start growing. And then as I go backwards to compute these derivatives, we can get what's called the exploding gradients problem, where the gradients just explode, they get too big. The opposite could happen if those numbers are much smaller than 1, then my signal is diminishing and diminishing and diminishing, right? So by the time I go back and work with the gradients, it says, well, changing the value here does like nothing, because by the time it gets to here at the output, my signal is so small. This is called the vanishing gradient. So you have to be very careful that these numbers are well scaled, and I'll talk about that in a minute when we talk about initialization. Because backpropagation here just has that one objective, it's a little bit easier to understand. Let me just show you a simple example. Let's do just multiplication, right? So let's say in comes A and B and out comes C. So I've got this function here, and typically it's gonna be something more complicated. We're just gonna do multiplication, right? And so we would call this the forward pass. In the forward pass, A and B come out, and what I do here is I would compute C, A times B, and I would return C. And that's my function. And I'm going to do something here. I'm going to return a cache, and I'm going to put A and B in there. Okay. That's maybe a little bit silly in this example because there's no intermediate calculations. But maybe let's say this operation is, well, I'm just going to leave it at that. You can imagine that some intermediate things happened here, and I just kind of want to save those variables, because what's going to happen is as I go through this network and I'm computing things and I move forward, I'm going to wait till I get to the end, and then back propagation, I'm going to run reverse mode AD backwards to the network. And so I need to know what happened here, pass it back through, and pass it all the way back to the beginning and say, okay, here is the sensitivities, right? This is how. Let's just draw a real quick network here. Right, here's all these things. And at the end of the day, I put all these things to get J. And once I get J, I need to work backwards to here to say, for example, what was the derivative of J with respect to X1, for example, and then X2 and X3 and so on. And remember, reverse mode AD is very efficient for one objective and many outputs. I can get all of these in one pass. Whereas if I was going forward, I'd have to do N passes for all the inputs. So here we're just looking at one operation here. Here's the forward. And now when I come backwards, I'm going to use a standard notation we use in the book, or the notation we use in the book, but which is standard for in the AD community, maybe not so much in machine learning community, but we're going to call C bar as the derivative of J with respect to C. Okay, so whenever I put a bar, it's the derivative of my objective, which I'm training on with respect to whatever output I have. So when I work through this, I know A and B. When I go forward, I know A and B, and I want to compute C. When I go backwards, what's going to happen is I am going to know C bar, and I need to compute A bar and B bar. Okay, so I'm going to have a reverse mode for this thing, which is going to pass in C bar, that's known, and I'm also going to want that cache back. Okay, and I need to compute A bar and B bar. Okay, so I have to do that. The backpropagation library or the reverse mode AD library has defined these for all the operations you would need, but here we're just going to do it. Well, that's not necessarily true. Sometimes we have to override our own, but for efficiency or things. But here we'll do this example for multiplication. We know that C is A times B, right? So I want to compute A bar, for example, and A bar is the derivative of J with respect to A. And the chain rule says, well, that's the derivative of J with respect to C times the derivative of C with respect to A. Well, this thing right here is this, right? So that's just C bar. And the derivative of C respect to A is just B. Right, so that's my formula there. So in this reverse function here, I'm going to say A bar is equal to C bar times B. And if I do that same derivation, I'll find that B bar is C bar times A. So now I'm going to return those things, A bar, B bar, and actually you can see why I wanted that cache here. I don't have B and A here. I will get cache.b and cache.a, right? I saved those values from the last class, or saved intermediate things that I calculated. Okay, so again, the idea here is that A and B came in and compute C out. I go all the way to the end, I get J, and now I start from the end, start with J bar, work my way up, I compute all the bars, I get C bar, and now this function needs to compute A bar and B bar. If I define that, and really this is easy for a neural net because every neuron does kind of the same thing. I mean, there can be different activation functions and so on, so we have to define those, but same kind of thing done over and over again. So this ends up being relatively straightforward. So how do we start it? Of course, at the beginning, we know how to start inputs. We give it at X, go and compute J. Here we give it J bar, right? But J bar is, by definition, it's DJ, DJ. So that's just one. So we just pass in the one for J bar, and out of this last layer, I get, you know, the derivatives from that layer, and I work my way back. Okay, so that's backpropagation. Mini-batching is this idea where if I have lots and lots of data, which is very common in the computer science community, it depends on your use in the engineering community, whether you have tons and tons of data or not. But the idea is that computing those gradients can become very expensive. So for example, the objective, and I guess I said I was going to use J, so I'm going to stick with J. J is going to be equal to 1 over n times I equals 1 to the n of some loss function, okay? And the loss function we did before was mean squared error. There are other possibilities, but it's going to be something like this form. If I look at this, I can see that this is an average, right? And I should be clear that, oh, shoot, we don't always put the 1 over n, but I could do that, and that wouldn't change my answer, right? It would change the value that I would compute for my objective, but not the optimal solution. But this is an average, right? And we know from statistics that if I'm computing the average over this really big sample, that I could also compute it over a smaller sample and get a reasonable estimate. And so where this really becomes a challenge is that what I'm going to need is the gradient of J, right? I need that derivative, those gradients, and that is also going to be 1 over n times the sum of a whole bunch of gradients, okay? And so here's the problem. Let's say n is 1,000,000. I've got 1,000,000 data points. Then I've got to compute the derivative of that loss function for 1,000,000 data points, which is a whole lot of gradients to compute, and then sum them up, average them, and return that. But as we mentioned, I don't necessarily have to do that to get a reasonable estimate. I could approximate this as 1 over m, where m is less than n. So let's say n is 1,000,000. Maybe I'm going to break it up into batches of 1,000 or 100 or something and give myself an estimate of that gradient. So pictorially, here's what that might look like. What I would do is we've got all of our data, and like before, we would divide it up into some training data and some testing data. Sometimes people divide this further into two sets, what you might call like a validation set and a testing kind of set. And one would be you'd be using during the training to compare, see how I'm doing on my test set, and the other you would not use, right? And you would only use that to compare as an unbiased estimate. But what I would do in mini batching is I would take all this data and I would randomly permute it. So here I'm just showing that conceptually with colors, but in a programming sense, you'd probably just permute all the indices, reorder the data, and you'd have to reorder the labels correspondingly, and then break them up into batches. So conceptually, all I'm doing is just randomly shuffling the data and breaking them into batches. I don't want to do them in chunks just because they might be ordered in some way. And so that would, I want my gradients to give me the best statistical sampling just to kind of be random here. Right, and so then I use those batches, and then I'm going to compute gradients on only this little piece, as we talked about here, and then I can take a step, move forward, go on to my next round and do that again. And so my gradients are going to be a little bit more noisy. In the extreme case, actually, I could take one sample. This is stochastic gradient descent. But typically in a mini batch, I could do something, it could range from 1 to my full set or something in between, right? So I've got an option here. All right, so initialization. I mentioned that the problems with exploding and vanishing gradients. So if you've got a small neural net, you've got only a few layers, this doesn't really matter. But, well, I should say it does matter that you initialize things randomly. What will happen is if you just put everything, let's just say I make all my weights, I just make them all zeros, or let's just even say I make them ones. And my biases, those can actually stay as 0, but let's say I keep all my weights as ones. That seems like a reasonable thing to do with no other information. The problem with that is that these neurons, we've laid them out, are symmetric, right? So if I take, let's just look at this neuron here, X at that layer is equal to the weights from the, so let me just give these some names to make this easier. Let me call this X1, X2, this will be X3, and X4. So forget about the activation for a second, but well, I can put it in. X3 here, X3 is going to be some weight, call this weight 1, 3 times X1 plus weight 3, 2 times X2 plus a bias, just call this bias, whatever, 1. And then I put that through an activation function. Okay, now X4 is this next neuron, and it goes through an activation function, and it's going to be weight, what is that? 1, 4 times X1 plus weight. I feel like well, this is 4 and 2. I haven't been very, oh yeah, that's fine. Plus B1, and let's say these B's are all 0. So notice if I make all the weights the same, all the X's are same. I mean, they could be, X1 doesn't have to be the same as X2, but they're the same in these equations, right? Because I'm going to sum up X1 and X2. I'm going to sum up all the nodes on the other layer. So if all these weights are the same, then X3, X4, X5, they're all going to be the same. The next layer is going to be the same. And my network is going to be severely hampered, right? It's basically like I've only got this outer section here. So I need these weights to be random. I can't have them just all be constant. But if I make them just all random, and I'm not careful about the size of them, then I get those exploding, vanishing problems of gradients. So I'm not going to derive this or motivate this really. You can go look this up. But one common strategy was first developed by Xavier and later modified by Hugh, who modified it for, well, so this one I think was developed for either the sigma or the tan-H activation. This one is for the ReLU, which is more common, so I'm just going to show you that. And what we do is we take all of our weights, and they should be randomly sampled from a normal distribution with mean 0, but a standard deviation of 2 times the number of layers coming in, and the biases, those can all be 0. So in other words, if we do this simple example with 3 layers here and 4 layers here, the weights that are in these connections here, we would give it a standard deviation of 2 over 3, because 3 is the number of layers that are coming into this section. So I just randomly sample according to this distribution, and then that makes a huge difference. Okay, the last thing I want to talk about, and this is going to go through several steps here, is just talking about algorithms. And there are lots of other details related to neural nets, but I wanted to bring this topic in because it connects to things that we've done this semester, and so it'll be helpful I think it'll be good to make these connections. So gradient descent is really the same, basically exactly the same as what we call steepest descent. The only difference is, well, two big differences is that machine learning, or in deep learning, there's no line search. So let me just write it down, right? So gradient descent means that, and remember, theta is W and B. I've just combined them all together because I don't want to write two equations. It's just all my parameters. And actually, it's not just W and B for that layer. It's W and B for all my layers. Just concatenate them all into one big vector. And then I'm going to go my step size alpha, and then my gradient of my objective, right? That is just, and the gradient, of course, is with respect to theta. This is gradient descent, and in steepest descent, or in what we learned in class before, this we called the step size, and we did some sort of line search because we really wanted to be careful about how many function evaluations we use, because in the engineering context, most of these things are expensive. But here we're just trying a surrogate here in this neural net. That's not necessarily the case. And so in the deep learning community, this is called a learning rate instead of a step size. And it's typically fixed. It could have or it has a prescribed decay, or it doesn't even have to be decay, but it has a described, prescribed values. In other words, it's not something we're calculating adaptively based on our last gradients like we do typically in steepest descent. And we don't do any sort of line search. Okay, so we just, again, most typical is just pick a value, something like 1 to the minus 3, 1 to the minus 4, and just leave it at that the whole time. And that's something you have to kind of tune. In the deep learning community, they call that, or machine learning community, they call it the hyperparameter. But it's just something that you can choose different values for. Okay, so that's it for gradient descent. And all of these methods I'll talk about you could use with batches or not with batches. And so you might call it stochastic gradient descent if you're doing really small batches. Before going on to the next method, I need to briefly explain exponential moving averages. So, because it's something we're going to use. An exponential moving average is well, to motivate this first, remember the main problem with steepest descent is that we bounce around. And we showed that if you took the optimal step, you would be moving in orthogonal directions every time, right? The dot product would be 0. And in practice, of course, you don't take exactly optimal steps, but you do tend to overshoot. And if you don't, then probably the next step you will. And so you bounce around a lot. It's pretty noisy, assuming that the conditioning of the Hessian or the contours, the curvature of the space is not equal in all directions, which it never is. That would be great if it was, but that's really hard for it to be scaled perfectly in all directions in the entire, across all iterations of your optimization. So the motivation here is let's try to smooth that out. The gradient is bouncing around, and maybe even more so if we're using these mini batches. Let's try and smooth it out by doing a moving average. Moving average, the idea is, well, let's say I'm driving a car and I want to look at my, I was going to say velocity, but that's going to get confusing, but I'm going to do it anyway. Here's my velocity. I say it's going to be confusing because I'm going to use that same word. Sorry. Here's some data points, and it's a little bit noisy, right? Like, yeah, I'm not going to use velocity. Let me pick up a different example so that I don't confuse two words here. Let's just say I want to look at the power that my wind turbine is producing over time. And wind is constantly fluctuating. So there's some mean patterns here, but there's also just a lot of noise. I should put this around here because of turbulence, right? So it's fluctuating around. So maybe if I want to plot that power, I don't want to keep plotting. Oh, it's 3.62 kilowatts. Oh, it's 3.81 kilowatts. It's 3.71 kilowatts. Like it's bouncing around too much. I want to kind of smooth it out and see some sort of average. And averaging, of course, is easy to do. I can just, oops, that was terrible. I can just I can do what's called the moving average because these are coming in time. I could go all the way back in time and save all these values, or I could save the last 10 values and average them together. But that takes more memory. And in our context, we've got a lot of parameters. And so if I've got to multiply that by 10, that's going to really kill my memory. So I'm going to do something else called an exponential moving average. And what that means is, let's say I wanted to predict that power. I'm going to say my power is going to be a weighted sum of my last power. So this will be at, let's say, t and t minus 1 here, plus the power that I'm measuring right now. I guess I should call this something else instead of power. This would be like my average power. Okay, something like that. So the benefit here is I only have to remember one number. Okay. And I get an instantaneous measure of power. I've remembered my average, and now I update my moving average. And that's the only thing I save. It's just that moving average number instead of saving the last 10 values or something. So, and that achieves almost the same effect. We could write that out and see how that would work. So for example, let me just write out a few terms here. Let's say I'm at power 10 is equal to beta times power 9 plus 1 minus, or my average power, times my instantaneous power at 10. But the average power at 9 was beta times the average power at 8 plus 1 minus beta times the power of 9. So I could plug that into there. And so we'd say the power of 10 is equal to beta squared times the power times the, sorry, I'm confusing myself, times the average power at 8 plus beta times 1 minus beta times the power of 9 plus 1 minus beta times the power of 10. So if I kept expanding this, right, I'd get something like beta squared, 1 minus beta times P8. I'd get beta cubed times 1 minus beta times power 7. So what you can see is that it's discounting all these former ones. So I've got 1 minus beta times my current one. All of these have a 1 minus beta, but then I've got multiplied by beta, beta squared, beta cubed. So beta is like 0.9, for example. Pretty soon these terms are very, very small. But instead of actually having to save all these numbers, I didn't have to save 9, 8, and 7. I just had to save my current running average. Okay, so that's the exponential moving average. We're going to use that to help smooth out our gradients. The other thing we are going to want to do that we'll use is to try to remove the bias. And so what that is, if I draw that plot again of the power of my wind turbine, try to draw it a little better here. Let's say it's kind of noisy like this. Okay, my exponential moving average is actually going to look something like this. It's going to be kind of way off at the beginning, and then it's going to get pretty good as I go. The reason why it does that is that to start, I'm going to now use v because that's organized later velocity. I'm going to initialize it to 0. And so my next one ends up being, sorry, I'll just keep the same ones that I use not to get confusing. My average power to start is just 0. My average power at the next step is going to be 1 minus beta times the power I measure at that first step, and then plus beta times my average power at 0, but that was just 0. Okay, so already you can see that this is going to be a problem. So let's say beta is 0.9. So beta is 0.9, then the first average, first of all, I start at 0, but then I start, because I know nothing, right? I don't have any information yet. I haven't collected any data. But then in my next step, I've got 1 minus 0.9, that's 0.1. So I take 0.1 times my current measurement. Whatever I put in there, it's not going to be a very good average, right? Because whatever I put, it's going to diminish my power. So I'm going to be way underestimating whatever the next one is. And that's just going to keep compounding. Power of 2, or not keep compounding, it's going to occur for a little bit. Get 1 minus beta times power of 2 plus beta times 1 minus beta times the power at 1. And so again, all of these coefficients don't add up to 1. Before, when we're doing the averaging, the way we do it, this formula is beta and 1 minus beta add up to 1. That's by design, right? I'm getting kind of a linear combination of these two. But here I have 1 minus beta times, I would have had it because beta's here, but this is 0. And same thing here, right? I would have a linear combination that adds up to 1, but I've got this term here, the beta squared, I guess. Anyway, it's the term with the P0 and it's gone, right? So yeah, the beta squared 1 minus beta. But it's gone, so yeah. So my average is a little bit off. But we can see a pattern. If I go to P3 and I just write out the coefficients, it's going to be P bar 3 is 1 minus beta plus P3 times 1 minus beta times P2 plus beta squared 1 minus beta times P1 plus the term that would have been P0, but that one's gone. Okay, so I really want those coefficients to equal 1, but they don't. If I added them all up, I would see I get 1 minus beta, that's this first one. And then if I add this next one, I get plus beta minus beta squared. And then the next one is this one, plus beta squared minus beta cubed. And what you can see is that those inner pairs are always going to cancel, right? Those cancel, those cancel. So I end up getting 1 minus beta cubed. So in other words, if I had taken all these coefficients here, let me just erase this, and divided the whole thing by 1 minus beta cubed, I would have gotten these coefficients to now sum to 1, and I would eliminate that bias. So in general, then the formula is going to be, if I want to measure this average value, and I'm going to use a hat later, actually, so I should have kept using that. I get what no, sorry, this is the unbiased one. The unbiased one is the average that I measure at, say, step T. Here, this is step 3, and I've got a 3 here. I divide by 1 minus beta to the T. Okay, this gives me what's called the unbiased estimate. And so if I do that, then I get kind of the right behavior at the beginning. This is really only important at the beginning. Notice as T gets really big, this number is going to go to 0 because beta is less than 1. So I'll just get my average power. And that should make sense because as these terms get longer and longer, the significance of having missed that one term is not important. But at the very beginning, it can be important. Okay, so that was a lot of kind of background to get to what's called momentum. Momentum says, well, gradient descent, bouncing around a lot. Let's try to smooth that out by taking a running average of our gradient. So we're going to call this V, sometimes called like a velocity, and it's going to be this running average of our previous one, right? 1 minus beta, and this is going to be the gradient of my objective. So what you can see is that this is an exponential moving average. It's this running average, right? I take my objective, V starts with 0, so that's gone. I just take my my gradient and I get a new average and I update that at the next time step and so on. So I'm just keeping a exponential moving average of my gradient. And so then my update rule looks the same. It's theta minus alpha, but instead of gradient of J, I'm going to use this V, right? And so that's it. That's called momentum. It looks, and actually in the literature, often you'll see it without this term. You don't necessarily have to have that term, right? It could be equivalent to just rescaling the objective because this is just a constant multiplied by my gradient. So if I scale my objective differently, I like to keep it there because first of all, it gives better intuition about this as a moving average, but also I feel like it better separates alpha, this learning rate, versus this beta, which is kind of this weighting between a moving average. But in any case, you might not see it there. And if I didn't put it there, actually, then let's just, for example, forget that wasn't there. This looks exactly like the conjugate gradient method that we've learned. It's the same form. The difference in conjugate gradient, though, of course, is that beta is something that we compute based on our current gradient, our previous gradient, and we kind of derived how that works. But momentum, just like the learning rate, is a fixed value, typically around 0.9, but it can be bigger or smaller. Okay, again, another hyperparameter you could learn. Okay, RMS prop is the next one I'll introduce, and this is building up to what's most commonly used. This is why I want to introduce these because it'll provide some intuition for the one that's most commonly used. RMS prop uses a different heuristic. Rather than using this heuristic about let's smooth out the gradient, it says let's smooth out the square of the gradient, or the root mean square of the gradient. That's what the RMS is. And the intuition is that if my gradient is really small, right, so I'm in kind of a flat region, then I should take bigger steps. And I should say it's not that the gradient is small, it's the gradient in a particular direction is small. I should take smaller steps in that direction. And so the idea is that if I've got these skewed curves, which I normally do, right, then I should take, it's pretty flat in this direction, so I should take bigger steps, but it's pretty shallow in this direction, so I should take smaller steps in that direction. So gradient is big in a direction, take small steps. Gradient is small in a certain direction, take bigger steps. The idea is let's take our root mean square of the gradient. So if I just look at the gradient, that could be positive or negative, but if I square them, add them and square root them, right? Then I've got this root mean squared, and that gives me some size of my gradient. And so if it's big, I want my steps to be small. So I'm going to put this root mean squared thing in the denominator. So if big thing's in the denominator, my step size is going to be small. So this is what it looks like mathematically. We call this thing S here. It's again going to be a weighted average because we're going to smooth it out. So we're going to take our last one here, weighted average of the gradient of j squared, and this is an element-wise squared. So I take every element in that gradient, square it, so it's positive, and now S is a exponential moving average of the squares of my gradient, and then my step looks just like we've had before. This is steepest descent or gradient descent right there, but I'm going to divide it by the square root of S. And again, the intuition there is that if the magnitude of these gradients, which, I'm kind of squaring these, keeping the average of them and then square root it, if those gradients are big, then it's in the denominator, it's going to make this step size here smaller. So gradients are steep in this direction, take smaller steps. Gradients are smaller in this direction, take bigger steps. And so it's going to kind of try to make my steps kind of point in a better direction. And the other little detail here is that we usually add some small number here, like 1 to the minus 8, just so that we never divide by 0 or something really close to 0 and make this blow up. Okay, last thing here, put this all together into what's called ATOM. ATOM is probably the most commonly used algorithm here for training these neural nets. Works quite well across many domains, so it's a typical default. And you could think of it as a combination of the two things we just talked about, momentum and RMS prop. So we're going to do exactly that. We're going to take the momentum term. So remember, it's a running average of my gradients. And here I've put a beta 1. Sorry, this is beta 1 because I'm going to have a different beta here. So this is V, and then this is S. This is the running average of my gradient squared, and it's got a different value. And so it's a different hyperparameter. We're going to call it beta 2. Again, just running average. These are the exact same things we just saw. Okay, again, element y squared and typical values. This is like 0.9. This is what's in the paper. This is, I think, 0.999. Again, running averages. What I didn't do in the other algorithms, which is done in ATOM, but you could do in the other ones, is to eliminate that bias. And so we're going to take v hat to be v divided by 1 minus beta to the t. Again, that really matters at the beginning, not so much later, but this is what the ATOM algorithm does. So I'm just writing it here for completeness. We already saw this. This is just to remove that bias from our exponential moving average that's inaccurate when we first get going. And then we put everything together in the same way. Theta is theta minus alpha. And this is the velocity term, right? This is my running average. This is exactly what momentum looks like. But then we also take that rule from RMS prop here and put a square root of my root mean squared of those gradients, and then add the little small term there. So that's ATOM. Relatively simple compared to the constraint, certainly compared to the constraint optimization algorithms we've learned, but effective for these, or seems to be effective for these deep learning problems. Okay, so that was it for today.